Welcome to section 9.2, expressions with variables. Do the problems with me, you try problems on your own, watch the video as many times as you need to, pause the video often. These are the topics and objectives, the standards, vocabulary, and concepts. So algebra is a super powerful tool because it allows us to reason about infinitely many calculations all at once because we have variables. In this section, when we study variables, we have to decode the letters and words just like we're reading English. So think about math as learning another language. We're decoding the variables and expressions. So what is a variable? A variable is a letter or any symbol that stands for any number with a specified or understood set of numbers. For example, a circle with a radius of r has an area of pi r squared. R is a variable that stands for any positive real number for the radius. It wouldn't make sense for r to be negative because we're talking about area and circles can't have negative radius or negative area. So it is really important when we define variables. So this is a really important concept here. You're going to see me use the number of or the amount of. And so when we define a variable, we don't want to say water, okay? Because we don't know what units we're talking about. We don't know what's going on. We want to say the number of liters of water in a tank. We want to be super specific. So we don't just want to say water. We want to say the number of liters, the number of milliliters, the number of ounces of water, okay? So again, we usually use number of. So number of liters, T could represent the number of minutes, or you could say T represents time, minutes. P, the number of people. S represents the number of small cups. L represents the number of large cups. So we wouldn't just say small cups and large cups. So when we are dealing with an algebraic expression, remember 9.1 was numeric expressions, no variables. Now we're talking about algebraic expressions, or sometimes we just call them expressions, and they can have variables in them. So again, a numeric expression would not have any variables, and an algebraic expression would. So we can interpret the meaning the same way. So when we have 1,000 minus 10 times p minus 15 squared, we can evaluate it the same kind of way, where last time we looked at the addition or subtraction that separates all the other. We've got 1,000 minus the product of 10 times p minus 15 squared, or p minus 15 times p minus 15. So there are some additional conventions we can use. We don't usually put multiplication when we've got a number in a variable or a variable in a variable. So here we have 2x. We wouldn't say 2 times x. And then 3xy is 3xy. We also wouldn't say x2. We would put the number first. And traditionally, we wouldn't say yx. We try to go in alphabetical order. So these are just some conventions. And that's what they're talking about here. So for example, if you were to buy X pens and each pen costs $2, then the total cost would be X times 2. But we would write 2X. And then the 2 would stand for the cost of the pen and the X would be the number of pens. So let's look at an example. So Kenny has stickers to distribute among some goodie bags. When Kenny tries to put 5 stickers into each of the G goodie bags, we don't know, he is 2 stickers short of filling the last bag. Write an expression for the total number of stickers Kenny has in terms of G. All right, so let's just make sense of this for a second. So let's draw a picture. So Kenny has stickers and he's putting them in a bag. So we don't know how many bags. These are my bags. So we could have 1 bag, 2 bag, all the way to G bags. We don't know how many bags, right? G goodie bags. And so he's trying to put 5 stickers into each. So he's putting 5 into this bag. He's putting 5 into this bag. He's putting 5 in all of these up until when he gets to the last one, he's 2 stickers short. So what's 2 less than 5? How many would he have for that last one? 3. So, well, how could we write an expression here? So if this is G, this is 1, if this was 5, right, that would be 4. If this was 6, that would be 5. This is 1 less, right? So an expression here that could model this is we know we're putting 5, 5, 5. We're doing 5 times all the way up until G minus 1. And then at the very end, we're adding 3. So this is an algebraic expression, and there are many. This is one example of an algebraic expression to represent the situation. So Ted is saving for a toy. He has no money now, but he figures that if he saves D dollars per week for the next 4 weeks, he will have 1 more than he needs for the toy. Write an expression for the cost of the toy Ted wants to buy in terms of D. All right, so let's think about this. He's got $0 now, and then he is going to put D dollars in week 1. He's going to put D dollars in week 2, week 3, all the way to week 4. And then at the end, what he saves, it's $1 too much for the toy. So the toy costs all of his savings, but then he has 1 extra. So how much does he save each week? Well, how many? We've got 1, 2, 3, 4 D. That's what he's saving. But then the toy, he has 1 too much. So the toy must cost -1, right? He has 1 less. The toy costs what he saves for those 4 weeks, but 1 less. So that's an expression for the toy. Go ahead and give this a try. Press play when you're ready to see the solution. And that shows you 2 different expressions that could work here. So students sometimes have difficulty formulating expressions because we're working with a letter that stands for something unknown. So where they might be comfortable with 3 times 8, 3 times x is a little bit jarring because x is not a specific number. So making sure to get really clear on numeric expressions before you get into variables is really important. So let's talk about terms. We did talk about terms before. But when we deal with expressions with variables, terms are very important. And these are the terms that are separated by addition and subtraction. So we've got 2 different terms here. We've got the term 1,000, and then we have this term here. So there are 2 terms in this expression. Inside of a term, we have coefficients. So if we're dealing with variables, the number that multiplies the whole term is the coefficient. So if we had 3x squared, 3 is the coefficient because it's multiplying the rest of the term. 10 times p minus 15 squared, 10 is multiplying this entire term, so 10 is the coefficient. Sometimes we have a hidden or invisible coefficient. This is really 1x, so 1 is the coefficient. We would not say that there would be 0, because when we multiply something by 0, it actually becomes 0. So we would say it's a coefficient of 1. Let's take a look at this example. For each of the next expressions, describe its structure using mathematical terminology such as term and coefficient. So again, we're looking for the difference in addition and subtraction, but this does not constitute as a separate term because it's inside of a grouping symbol. So keeping that in mind, we're not just separating. We wouldn't say like this is a term, this is a term, this is a term. That would be incorrect because when we look at GEMS, right, we're basically separating everything up until this point. So we've got this grouping symbol, we've got this exponent, and then we've got this multiplication. So this is all one term. And then we've got our addition at the end. So using GEMS to help you, we would see that we have 2 terms. And this term here is a term, but it doesn't have a variable, so we just call it a constant. And we have a term here, and the coefficient of this term, what's multiplying the rest of the term, is 2. So here, if we look at GEMS, we don't have any grouping symbols. We don't have any exponents. Well, we have the exponents on the variables. And then multiplication or division, that's happening to each term. So this would actually be separated by these addition and subtraction. So we've got 1, 2, 3, 4 terms. And the coefficient here would be 5. The coefficient here would be -4. And I'm going to erase this so we can look at this a little more closely. The coefficient here is 5. The coefficient here is -4. The coefficient here is 3. And the coefficient here is -1. All right, so, and we would actually call this -1 a constant because it's not multiplying. But these would be our coefficients. All right, go ahead and give this a try. Press play when you're ready to see the solution. We can evaluate expressions And evaluating just means replacing the variables with numbers and then determining the number that the expression equals. And again, remember, expressions do not have equal signs, but we can still determine what they equal. So here we've got evaluate this expression, 3x plus 4y, where x is 6 and y is 7. So we're going to replace this x with 6, and we're going to replace this y with 7. So it will look like 3, and instead of that x, I'm going to put in a 6. And 4, and instead of that y, I'm going to put a 7. Now remember, when they're next to each other, that's multiplication. And I do use parentheses in general, and then we follow gems here. So we don't have any grouping symbols, no exponents, but we do have multiplication and division from left to right. So we've got 18. And you can do these simultaneously because of the properties of multiplication, but we end up getting 46. So we evaluated this using gems. So now we only have one variable here, but we have it in 2 different spots. And it's really important that we keep everything else. So I'm going to just copy everything but the x, and I'm going to leave giant parentheses. And remember, the x is 2. Now, when I do gems, it's really important. Okay, grouping symbols. Remember, when we look in the parentheses, there's no operations to be done inside, so that's over. Then we look at exponents. I'm going to deal with this exponent first. So I'm going to bring everything else down. And 2 to the second power is 4. And I've dealt with my exponents. Multiplication and division from left to right. So I've got this multiplication, this multiplication. So I've got 12 plus 10 plus 1, and addition and subtraction from left to right. So we'll go in this direction first. So we get 22 plus 1, and we end up with 23. So that is what this expression equals. Go ahead and give these a try. Press play when you're ready to see the solution. And that concludes this part of 9.2.